So it's a great honor to be here and talk to you about urban air mobility. But before I do, I want to say it's really great to be at Harvard as an MIT professor, and we like to tease each other. So you know about Central Square, right? It's right very close to here. And so there was a student shopping at the Star Market at Central Square, and the student was piling his cart full of items, and then went to the express checkout lane where it said 6 items or less, and the cart is full. So the cashier looks at him and says, either you must be from Harvard and you don't know how to count, or you're from MIT and you don't know how to read. So I'm here to count, and I'd like to start this with a somewhat sort of quantitative perspective. So we're going to hear about these great designs. This is an example from a competition that Uber ran last year, and so I think we're going to hear a lot more about the infrastructure that's needed to support future urban air mobility. You can count the number of vehicles that are on these different platforms. It's about 36, and so keep that in mind. 36 roughly. Drones that are all either taking off, taking on passengers, recharging. And so I think to discuss urban air mobility with some realism, I think we need to think about what does it take physically, how many vehicles, how much capacity can such a system support, will it make a difference? And so I think the major questions around urban air mobility fall into 3 categories. The first one is technological. I mean, I listed first because as a professor of aerospace engineering, this is usually what we think about first. So these vehicles, and many vehicles have been proposed and prototyped, and that's very exciting. Kind of reminds you of the first days in the automotive industry where we had, steam engines and electric cars actually over 100 years ago. That's kind of the stage that we're at. So range, payload, safety, noise, cost, what are really requirements to be successful? The second is then when you go from individual vehicles up to the fleet level, to the system level, what is the expected capacity that you could expect from a full-fledged urban air mobility service in a typical large city? What's the fleet size? Can it be profitable? And then the third questions are more the social questions, where I think Aero Futures really helps us think about the social environment. What are the hurdles for adoption in urban environments? Noise, traffic management, laws and regulations, but also things like public acceptance and willingness to pay. So my belief is that we can learn a lot from simulation, simulating different futures in different cities. We can't learn everything from simulation, but it helps us bound the problem. So let me start with a very specific example. So imagine that this is our sister city, San Francisco on the West Coast. You just landed at SFO Airport, and this is data from a particular day, so about a month ago, 26th of March, 2018, so about a year ago. 8 a.m., you land at San Francisco Airport. And you'd like to go downtown. In this case, we want to go to Pier 39. So there's the public option, public transportation, of course, but you could also take an Uber X, ground-based, a taxi, and that will take you anywhere. You see the different routes between 35, 40 minutes to about 70 minutes. So I'm going to look at the worst case here, because fundamentally what urban air mobility is about is the differential advantage that urban air mobility gives you over ground transportation. And you'll pay about $58 for that Uber ride. Or, and this is what urban air mobility is promising us, you can get there in 8 minutes. So this is a possible route over the water, makes sense. 4 waypoints, that's an 8-minute flight. In a Robinson 44, which is a very successful commercial helicopter. And how much would we charge for that ride? And so there's quite a bit of research around this. To keep it simple, most of the research indicates that perhaps $1 per minute saved is a premium that the market might be able to yield over the ground transportation. So we would pay about $120 for that 8-minute flight. That's probably an upper bound. Here's another route, again in San Francisco, airport to airport. So it was very interesting to hear the discussion and the focus here on airport design. So San Francisco has 3 major airports, SFO, Oakland, and then San Jose. So if you want to get over to Oakland Airport on the ground, that's a very similar trip, also about 70 minutes, a little more expensive, $71. That's a great route for urban air mobility. You just fly across the bay. That's a 6-minute flight, potentially $135 fee. So we're not interested just in individual routes, but urban air mobility, and this is, I think, an interesting debate. Do we just cherry pick the most interesting origin-destination pairs and that's good enough, or do we create a whole citywide network? I think that debate is still ongoing, but I think most people think that we should create a network. And so here's a potential minimalist network for San Francisco. There's 11 different, the red dots, each of those would be one of those vertiports that you saw, about 38 different routes. You don't have to have a fully populated network, but for the most popular origin-destination pairs, of course, you would like to have direct routes. So it could be very promising. San Francisco has the 3rd highest GDP per capita in the world, heavily congested. Those of you that have driven on the 101, you know this. Prominent landmarks, key bridges that act as bottlenecks. Also, I think a city that's very accepting of new technology. The maximum distance in this network is about 75 kilometers, 11 origin-destination pairs, and about 38 routes. And the other thing which is important, we have very good competitive information from the competing ground transportation modes like UberX and public transit. So this is a prototype of an urban air mobility simulation that we developed. Without getting into too much detail, it's fairly straightforward. You need input information, and that's a city file. You need to describe the city of interest in terms of waypoints, this origin-destination matrix. Also understanding traffic, what's the traffic like in that city today, peak hours, off-peak, nighttime, ground competition, both in terms of time and cost. Then a vehicle library. And so there's a lot of these vehicles that have been proposed. Urban air mobility already exists today. Many of you are aware of this. You can already fly with helicopters in certain cities. A vehicle library where these vehicles are described in terms of things like range, payload, and so forth. Then think about the routes. So for each route, you calculate things like time of flight, feasibility, energy consumption. The traffic model is probably one of the most interesting areas for research. Do vehicles go back and forth on the same route? Is it truly an on-demand service like we see with Uber or Lyft, for example? The economic evaluation, and then finally the results, which is which vehicles can be successful in what city, cash flow, operator net present value, visualization, and of course environmental impact as well. So I don't have time to get into a lot of detail. I just want to give you a feel for what these simulations are telling us. So here's San Francisco and 3 other cities that we looked at, Paris, Beijing, and then Sao Paulo, where Airbus has been running its VOOM service, which is really also an experimental platform for urban air mobility. Just a couple on the cities, a couple of the really interesting, it's not just about the city center, but also quickly getting to points in the periphery. So Paris, of course, you have, for example, Versailles on the west side. You have Disney Paris. You have the airports, Charles de Gaulle, Orly in the south. Beijing, very interesting. The point in the northwest, that's the Great Wall of China. In the south, you may not be aware, but Beijing is currently building what will be the largest, by far the largest airport in the world that will become operational within the next couple of years. So that's a very big deal. And then Sao Paulo is a bit sparser as a network, but we do have current data on actual urban mobility for Sao Paulo. So for each of these cities, the question then is, well, how far are these routes? That's the first thing you need to understand is, how far do we fly in these origin-destination pairs? And even though those cities are all very different, once you start overlaying these route structures, so this is the fraction of routes covered by a certain distance, you see that things start to look more similar. And so if you want 80% coverage in San Francisco, you need a 45-kilometer range. Beijing, you need a 57-kilometer range. Paris and Sao Paulo are a bit more compact. The other thing that's really critical, and I think this is one of the most interesting questions, is how many vehicles would you operate on each route and in the city? And to understand that, it turns out that the number of vehicles depends on these three key variables. Time of flight, so how long does it take you to get from one point to another? The turnaround time once you're on the ground. And what a lot of people don't think about is in the denominator in this equation is, I promise you that's the only equation in my talk, is the separation time. What is the minimum separation time between two air vehicles on the same route? It's absolutely crucial variable in this problem. So basically we're talking about something like this, where vehicles would follow each other at some minimum separation distance as they fly each route, and that will be the key sizing of the vehicle fleet for the whole network. So what are we learning from this? So for different types of competing vehicles, so you have the eVTOL. So this is somewhat anonymized because we think this is pretty sensitive information. So I just want to give you a general feel for, there's 9 different competing electrical vertical takeoff and landing vehicles, and then 3 existing helicopters. So the helicopters actually don't do too poorly on this if you don't consider noise. So what we're seeing is about typical fleet sizes here of about, let me go back here if I may, 200 to 700 vehicles per city, depending on the type of vehicle. So that's a typical fleet size. The other thing that's very important is how much does it cost to operate one of these vehicles? So anywhere between $100, $200 to $700. Daily profit. Can you make money operating urban air mobility? And the answer is not straightforward. So some cities seem to be very well suited. Paris, for example, looks quite promising, and other cities much less. Surface area. How much surface area do we need? It's quite considerable. So the blue line that you see here is about 10 soccer fields, and this is, of course, in prime locations. So is that real estate available? So let me finish by saying that from these simulations, we do get some key insights on technology targets, so the size of these vehicles, the minimum ranges we need, turnaround time, absolutely critical, fleet capacities, the number of flights. This could be a lot of flights, 2,000 to 20,000 flights per day, but even at that level, we're well below 10% market share. We have to keep that in mind. And then there's many hurdles to adoption. So with that, those of you who are Star Wars fans, you know what this is, right? Coruscant. Maybe we're headed that way. Thank you.